Here I have a really small sample of pitch blende, which is just a mineral. This one is from Cornwall. And this has just been dug out of the ground, hasn't been touched or played with, interfered with in any way. But look what happens when I place it near my Geiger counter. It is naturally radioactive. In fact, it's not the only rock. We've got some other samples here. We've got a rock called Tobanite from the Congo. Also very radioactive. In fact, all of these rocks in here are examples of naturally radioactive minerals. It turns out that the whole world is made out of rocks that are to lesser and greater degrees radioactive, depending on how many unstable isotopes they have. With these particular minerals, they just have a lot, and that's why we can detect it. But this radiation coming from the rocks underneath our feet is actually having an effect of creating a background level of radiation that we experience every single day. We can investigate the background radiation with something like this. This is a portable equivalent to a Geiger counter. It tells us the amount of radiation that we're detecting right here. And right here, close to the ground, we are measuring 0.09, and then there is a unit for the amount of radiation. This one is microsieverts per hour, don't worry about that. But if I move to a different place, I might find that the background radiation was different because I was closer to one of the sources of background radiation. Now, we've already seen that the rocks themselves can give off radiation. Here, the rocks are not that radioactive, but there is something coming from those rocks that is. Here, further from the ground, I'm experiencing less radiation. I'm further away from those rocks that are giving out radiation, 0.06. When it comes to sources of natural background radiation, by far the biggest contributor to the dose that we receive is coming from the ground, but it's not entirely the rocks. Now, I'm here in a big old house, and I want to take you to a place where we might actually detect some of that background radiation. To do it, I'm going to need a torch, because we're going underground. I have with me the rad counter. At the moment, it is reading 0.2 microsieverts per hour. So there's quite a high amount of radiation here compared to when we were on the science roof earlier. So I'll put the torch on, and we'll go for a bit of a journey down into the underworld. So we're going into a cellar here, and we're going to look to see if the radiation level increases as we go into this environment. You can see it has jumped up to 0.24. Not 0.25. There is definitely more radiation down here than there was up at the surface. So why is this? Down here in this cellar, the ground is slowly allowing some radon gas to seep through. Radon gas is a substance that is radioactive. It's produced deep underground by rocks, and what happens is it is slowly moving up through the porous ground, and it is getting trapped in this space. That is why it is more radioactive down here than it is at the surface. You can see an air brick up there. That is an attempt to allow it to vent properly. But if I were to carry on getting higher and further away from the ground, it wouldn't continue to go down. Eventually, right up there, I might experience that the radiation that I'm exposed to is starting to go up. And this is because the Earth is bombarded by radiation from space. Cosmic rays are basically radioactive particles that hit the top of our atmosphere. Most don't get down to us here on Earth, but I only have to go up in an aeroplane for me to experience radiation dose from the sky. You know, all of the food that we eat contains a small amount of radioactive material. 11.5% of our background dose comes from things like bananas. Oh, show brain. What might be really useful at this stage is to explain the 3 different words that we might use to describe different types of radiation. If you see here, radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays, these should be familiar to you as the electromagnetic spectrum. So all of these are in the same family of radiations. They're all EM, electromagnetic radiation. All of the same family as light. But what you'll notice is that here, alpha, beta and gamma, well, these fall into a different category. These are what we would know as nuclear radiation. Because these 3 can be given off by an unstable nucleus, whereas these are not given off by unstable nuclei. The gamma rays are both electromagnetic and originate from the decay of an unstable nucleus. One final thing though is there's an additional category that encompasses all of these. All of these are ionizing radiation. It means all of these are potentially very harmful to human beings. And we'll talk more about how they're harmful later. All of these are not harmful to human beings, not in the same way. Now, some of the background dose of radiation that we receive comes from sources that are nuclear in origin, but we also experience radiation from these 2 as well. Most noticeably, we experience X-rays by going to the hospital, and this actually counts as part of our lifetime radiation dose. Here I have an X-ray tube. This sits inside the machine that directs X-rays at your body if you have a broken leg. What develops on the photographic film placed beneath your body is an exposure showing where those X-rays have hit the film. Your bones have absorbed that ionizing radiation, just in the same way that aluminium has absorbed the beta particles. The X-rays have been absorbed by the high density calcium of your bones. And so therefore, just by looking at this image, you can see that you have absorbed a radiation dose by just having a medical X-ray. On August the 6th, 1945, the Enola Gay American aircraft dropped an atomic bomb on the Japanese city of Hiroshima. 3 days later, dropping another bomb on Nagasaki. This bomb contained radioactive material that was spread into Earth's atmosphere. And since then, thousands of bomb tests have gone off around the world, leaving a small amount of residual radiation. About 0.2% of our background exposure comes from the testing of atomic and nuclear weaponry. On April 26th, 1986, the Chernobyl nuclear power station in the USSR melted down, releasing a huge amount of radioactive material into the environment. It's not the only release, but it certainly is the most long-lasting and damaging. Here we have a postcard from the exclusion zone itself. Now, that accident and others like it have been putting radioactive material to small levels into our environment. This here is high-grade nuclear waste. This is part of the Sizewell A reactor, which has been decontaminated so that I can hold it. Now these contribute to about 0.1% of our background exposure to radiation. you can see from this pie chart that 50% of the radiation that we're exposed to over our lifetimes comes from radon gas, like we found in the basement. There are other sources represented on this pie chart as well, the food that we eat at 11.5% and cosmic rays at 10%. Of course, that is going to be larger if you're an airline pilot because you're closer to space. The rocks beneath our feet at 14%. And of course, over our entire lifetimes, X-rays, radiotherapy and other uses of radiation in medicine would result in us getting a dose of about 14% from medical sources. There are the more dramatic ones, the nuclear weapons testing and accidents with nuclear reactors, but they really represent only 0.3% together of the total background radiation. The conclusion is that we're exposed to radiation all the time. In fact, our bodies are quite used to it. But what we do have to consider are those situations where we're exposed to excessive amounts of radiation. And that's the topic for another video.